There's an example there, but I like this example. You'll be amazed that I like this example because this is one that I actually worked on in real life. And you can see that the notes were written by someone else who's talking about me. I didn't write about myself in the third person like that. But I really appreciate someone including this example in the notes. I think I've talked about it a little bit beforehand, but let me draw a diagram just to illustrate exactly what's going on here. So this is a sort of, this is a general diagram, but let me add a another picture. So imagine you have a network which looks like this. Call this node 1, node 2, and node 3, and we have a switch in the middle. That's the thing that sends packets or data in the right direction. And imagine that I can measure how much traffic and likewise, this is going to be Y3, this is going to be Y2. So imagine I can measure those things, and in practice on a lot of computer networks, that's pretty easy to do. Uses a protocol called SNMP, the Simple Network Management Protocol, and you could probably set that up yourselves on your own home network with a few hours work. It also scales pretty well. So, you know, a realistic network, a realistic backbone network for North America might have, say, you know, thousands of nodes or endpoints and tens of thousands of links. And tens of thousands is okay. I can measure tens of thousands of something. But it's not what I really want to know. For a lot of optimization problems across networks, a lot of network planning problems, what I would like to know is the flows of traffic. So imagine I call this X1. It's the traffic going from node 1 to node 2, and the traffic, say, going from node 1 to node 3, I'm going to call X2. Those are the things I would really like to know, but those are actually much harder to measure. And that doesn't scale as well, because if you think, if I've got n nodes, then I have n squared pairs of nodes, or rather my traffic matrix is an n by n matrix. And that means that if I have thousands of nodes, then I would have millions of paths or routes or whatever you want to call them. So that's much, much harder to measure than measuring each of the links. It's harder both technologically speaking and just from the sheer point of view of how much data I might have to collect. So what do I do? Well, let's have a think about this link here. Notice that the traffic Y1 is going to be the traffic X1 plus X2. It's the sum of all the traffic that goes across that link. And I can come up with a similar sum for Y3 and a similar sum for Y2. So what I will get is a series of sums which express the Y's in terms of X's. Now I can take all of those sums and pile them together in vector matrix notation and get something that looks like this. That's what we have here. It's then just a question of solving linear equations, you might think. But there's a whole lot of reasons why it's a little bit more complicated than that. One of them is that typically you have Y is the number of links, or the length of y is the number of links. And remember that's, order 1,000. And the length of x is the number of paths, which is order 1,000,000. So actually, this is under constraint. But there's also noise. There's errors that creep into any set of measurements. And that means that it can also be ill-posed. It could mean that there's no solutions to it. So you need to come up with a technique for solving this in the best possible way, given the data you have. The notes list this. Really, that was actually our first attempt. That's not where we stopped. But if you do this, this is a good start. What we're trying to do is use those equations constructively as constraints and minimize the distance between hypothesized values of x and this xg, which is a prior model called a gravity model. And you can see, I hope, that that's a quadratic optimization problem with a set of linear constraints. One way of thinking about that is there is a space of possible solutions, and I've just drawn that as a diagonal line here. The gravity model doesn't live in that space, but what we're doing is projecting down onto the space. And that's a really common way of thinking about a lot of statistical estimation problems, is projecting it into some sort of space. What else do I want to say about this? Well, the actual way you solve this, so this is kind of the first attempt solution. And there's all sorts of problems with this. But the one that is one way of thinking about this that's really helpful is to reframe this as a new optimization problem. Minimize, or actually what we do is we take argmin of x. That means take the value of x, which minimizes. So in mathematical terms, argmin is a lot like what we say when we just say minimize blah in words. But this is more mathematical notation. Argmin of x such that ax minus y squared, that's that L2 norm again, plus lambda times the distance between x and some model of x, mx. And so we can put it into that sort of frame. And why is this a good idea to do this? Well, you also have to have x greater than 0 because it's can't have negative traffic. So x must be greater than or equal to 0. So why is it a good idea to do it this way? Well, firstly, now I have flexibility. I can choose any distance metric I like here. And that's really useful. Turns out the distance metric that worked really well is a thing called the Kullback-Leibler distance. I don't expect you to know what that is, but it's an idea that comes from information theory, and it turns out to work really well. And just to emphasize approximation, it's approximated well by a quadratic, but not that quadratic. So we use a weighted quadratic to approximate the Kullback-Leibler divergence. And it's still a constrained problem because you have x greater than or equal to 0, but it's actually a simpler problem as well, because we have fewer constraints. We're only worried about x greater than or equal to 0. We're not worried about all of those other constraints. The other thing that's really good about it, though, is it acknowledges that there could be noise, errors in the measurements. And what we're trying to do is trade off between the model that we have over on the right-hand side in yellow and the measurements which we have here. If the measurements were really accurate, we would try and focus on them. If the measurements have a lot of errors, we'd probably prefer the model. And this parameter in here called lambda lets you tune the trade-off for where you want to be. We used a program called PDSCO, which was written by a guy called Michael Saunders from Stanford, I believe. This was state of the art when we were using it. And I'm an old croc now. I was doing this back in sort of around 2000, 2004. So nearly 20 years ago. And back then, having a problem with 10,000 variables made it really challenging. So we really needed state-of-the-art code to solve it. But computers have improved by orders of magnitude since then, and optimization routines have improved as well. As you know, we've been talking about some of the improvements in this course, and I expect that actually you could do way, way better than PDSCO now with MATLAB's vanilla routines, the ones that it just has built in. By the way, I'm going to put up a little sheet that just describes some of MATLAB's built-in optimization routines that you can use to test your results or to test your understanding and so on. So I would not necessarily recommend you go out and look for PDSCO. In fact, I think the guys who wrote it made it obsolete and replaced it with a new code base some years later. Might just be called PSO or PCO. But if you look up Michael Saunders, I'm sure you can find the latest, greatest stuff he's got out there. And I just wanted also to give you a flavor of, scale of these problems that you can solve and the way it's improved over time and, what's real about these sort of problems and how you can twist them around and change the way a problem looks in order to make it have better characteristics or to reduce the number of constraints, trade-off between constraints and the objective function, and the various things that might be complicated and hard and the various things that might be easy. And sometimes, as we found, it probably took us about a year, I think, to get this working really well. And a fair chunk of that was munging data. Munging data always takes way more time than you think it's going to do. The data cleaning, the data pipeline, all of that kind of stuff is always really challenging. But a fair chunk of it was just rearranging this optimization into a form and structure where everything worked really well, really quickly. And in fact, once we'd done all of this, once we'd reorganized all of this like this, I feel like it was taking under a minute to solve the optimization problem, but I'd have to go back to my original notes and check that. By the way, we have a patent on this technique. The patent was only granted in 2009. It takes a long time for patents to go through the system, but yeah, this is one of the cooler things I ever got to work on.